Okay, so we have been doing systems of equations right here. Okay, so it's so the two would be the independent variable is still one, t usually time. Now there are two spatial variables, x and y, and then the naturally the interactions are way more complicated. Okay, so if we're only doing the Euler's method, then that just makes twice as much work for the computer. So that's really not much of a difference. This is the way doing qualitative analysis. Okay, and then we asked ourselves qualitative analysis, meaning that no computer, but rather from just analysis of the functions that we have. We ask ourselves which way does it go? The solution curve, it's a parametric curve. Which way does it go? There are four possibilities depending on the sign analysis of the f and g. It is sign analysis f and g gives a sign of x prime y prime, which means the directions either x goes left or the x or right, okay, or y that's up or down, and therefore the total of 9 possibilities. Okay, so so initially what we're looking at it's kind of it's two-dimensional analysis, but this is the data that we collect right here. That's the data. And then we put that data together. If it goes to the left and up, okay, so if it's left and up, then it goes this way. So it goes over here, northwest. Okay, so instead of 3, we have 9 possibilities, roughly the difference between dimension 1 and dimension 2. That makes a big difference once we start plotting. So here's I take the differential equation that I do not expect to hope to solve. Okay, that's the point. So x prime is equal to sine of y prime is a cosine of y. Where does it come from? Doesn't matter. But analysis of sine and cosine is very predictable. So it goes up and down, meaning negative, positive, which creates for the horizontal, it varies once again, left, right. If we go look at it, as we go vertically, the direction changes from left to right to left to right. Okay, if we go horizontally like this, the direction changes from up to down to up to down. Okay, so I'm not sure. Well, yeah. So them together, then there will be every time we progress from left to right, and something changes. If we progress from top to bottom, once again, the direction changes. Okay, and so the analysis is very much like analysis. It is similar to what? Similar to non-autonomous analysis for dimension 1. Okay, so dimension 1, the most of the examples we did in dimension 1 were autonomous, and therefore there was no difference as far as the solutions are concerned in the horizontal direction, because moving along the t-axis did not change anything. So, but if they were non-autonomous, then actually there are two active variables present, t and y, and it's very similar like the autonomous 2D. So autonomous 2D are similar to non-autonomous 1D. Okay. So the difference, of course, is that in the two-dimensional case, you can actually turn around and go backwards. Okay, so the cases, the non-autonomous case are still similar to this, but you can never go back because time progresses in one direction. Here we're hiding t is not present, and therefore x and y could point in any direction. So that's how we have nine possibilities. And so once you have these, I brought these together like this, okay. And now I know which way we're going. You can guess that kind of a turn. You can once you know directions roughly, then you can imagine what the curves look like. So it goes this way and then up and then back. Okay, so the vertical lines are we're crossing a certain line in a vertical direction as we have done before. So this is a sketch, once again, some rough sketch of the portrait of the differential equation, but this is like a photo, right? So if we run the Euler method, it is pretty close to the truth, even though it doesn't show the directions. But so you have to actually add that to indicate that we are going this way. Okay, every time. So once again, we invoke invoke uniqueness to demonstrate and make that clear that the picture themselves, especially Euler's picture, does not reveal that the graphs do not merge, but rather they converge because of the so in other words, we have asymptotes and they cannot merge because of the uniqueness. So that's something that we have not stated. Okay, so but nonetheless, that's the theoretical part. We did well. We did state it. So uniqueness. Uniqueness is present, and that's why when you have two curves that seemingly merge together, they do not. In fact, so over here, so this one it will go like this. This will keep going left right. That's a go a straight line, and then the other the one that approaches from below does not merge with it, but rather approach it asymptotically. Okay, so that's so in other words, the tools of calculus that we use are exactly the same in dimension one and dimension two. Okay, another example is very similar. So this one I did instead x prime is sine x. So they're very good this one, and how different the total picture is. So maybe this one is not. You can tell that the difference is seemingly changing directions all the time. But once you plot it with Euler's method, look at it. Look at the behavior. And the behavior is quite a bit different. So there is no asymptotic behavior. Okay, so it is. So the path goes from equilibrium to equilibrium. Okay, so equilibrium, that's what I mark here, the heavy dots. Equilibrium, which means that both f and g are equal to 0 in the middle, that dot. Okay, and then in a kind of alluded pattern, but nonetheless, every curve starts near the one of the stationary points, equilibria, and then moves to the other one. So that's the whole picture. And then it becomes interesting then that if you stay away from the equilibrium, this situation is very similar to what we had in dimension one. If you stay away from the equilibrium, what do you observe? The trajectory is kind of parallel. They're almost parallel. They go in the same direction. So that's in fact, you sort of kind of going back to your diagram, and you tell roughly which way all the trajectory go. Okay, so that one arrow tells you what's going on. Okay, so it is however look at so there are still a bunch of possibilities. And each once again each point is this way. So how many? It says 8 possibilities, right? So away from equilibrium, 8 possibilities. Right, so Y8, once again, the 3 by 3 table, so there are 9 possibilities. If I exclude the center, then I have 8 possibilities. Nonetheless, so that's away from equilibrium. That's number 1, but then now at the equilibrium. Okay, that's really interesting. Turns out that equilibria are the interesting points. The behavior, as you can see, is quite a bit different whether you look at them over here. That may be not very revealing, but this one definitely you can see how. Can you see different behaviors around the equilibrium? One based on these pictures. How would you say if I take this point? What do you see here? What's going on here?
We're all going towards it.
Yeah, so you can think of a word for it. Okay, from before sink. It is a sink, except we had a sink in a pipe, but this one is it will look more like a sink, right? Everything going towards it. If I pick this one. Everything away, remember the word. Opposite of the sink. Well, we can, not the faucet, but source. The source of where everything is coming out, is that it? Do you see anything else? Different behaviors from these two? So we have a bunch of sinks and that's a bunch of sources. let's find all the sources and all the sinks. So this seems to be the source as well, and this where is this? This is another source. That's another source, and then these are this is this. Oh, wait a minute. This is the sink. This is the sink. Okay, 6, and then sources are. This is the source, and this seems to be a source. Okay, I may have missed some, but you can see what's left. I didn't get, that's another source right here. Do you see what's left? What? Yeah, so the word we used was pass indeed. And as it's less so, it doesn't look like a pass anymore. Think about it. It's actually it's kind of a halfway between the two. There's some flow towards and some flow away in a kind of interesting pattern that you can. So how is it possible to go in here and go out there? And the answer is it does this. Okay, so you can see it on this picture right here. So the trajectories are going towards it, but also one of them goes towards it and continue on. But some of them might be passing very close by it, but never actually reaching. So this is probably good location. This is one of those weird points. They are either passes or we call them hyperbolic points. Where some of the most of the trajectory are pass close and then turn away from. Okay, so the similarity is why it's hyperbolic point, because the behavior is similar to the behavior of water on a settle point. Remember, settle point in calculus 3 especially, a surface that over settle or pants, crotch of the pants. That's another way to say. But if it's a mountain, then what happens is, so they're on the up on this side and down on this. Okay, like this. Okay, so like this. That's my settle point. And then what does water do? It sinks down from above towards the center, but then unless it goes straight into it, it will turn, and that's a typical trajectory will look like this. Okay, that's how the water will flow along settle point. So if it is a hill, right? So what colors did I use? So this one actually I was meant to make it green. Okay. So to emphasize, this is the settle point, the way I colored them. And then there is as I have an example here, I have red being the source. How does it's a source. No, wait a minute, that's the opposite. The source is like this. Okay, so a max. So the water will flow down like this. Then there is the thirdly is the sink, as one would think. Everything is going down. Okay, so these are the three behaviors that the differential equation exhibits. Primarily the basic ones. There are more convoluted ones as well, but basically that's what you expect when you have a terrain. Okay, so if you have a terrain, then you have these. You can classify everything into what? Either it is one of these special points, or they're generic points. And generic points, nothing special happens. Everything flows in one direction, roughly. But if it is non-generic, if it is singular, then there are these three possibilities: down, up, or kind of in this hyperbolic way. Okay, so passing way. Okay. So that's what we can hope for. These are the three possibilities, and then they will constitute our main analysis that we actually will be able to handle. At this point, so I skip this. So if you just read some more examples with complex behavior, so that once you start plotting them, all kinds of behaviors emerge, and they look somewhat complex, including that complicated spiral. Okay, so let's try to sort out what that we're trying to accomplish. What can we hope to accomplish? So one-dimensional vector field is this. So it's a pipe, and then we're talking about y prime is equal to f of y. And then the sign analysis, once again, this is dimension one. Sign analysis produces each direction, that direction, this direction was zero. And then the classification of, remember that we have produced is a qualitative analysis, gave us three possibilities. Okay, once again, source in the pass. Okay, so we also, that's done. Now what becomes important here is the same result came. So the qualitative analysis gave us three. Okay, and then so did what linearization. Okay, remember that's the point of linearization, how we knew that we were successful linearizing a differential equation is that it will produce the same possibilities as the original differential equation. So significant simplification, right? So if we have like this, y prime is equal to f of y, and then by some magic, we produce y prime is equal to ky. Solvable differential equation, and then a linear differential equation. The answer is naturally exponential, as we know. And then the only requirement why it works out, makes sense, is in the vicinity of the equilibrium points, the qualitative analysis will be the same. Okay, so same QA. Okay, so if you linearize, not linearize, the qualitative analysis is the same. So that's what we hope for. Okay, so that's what we hope for in dimension two. So this is my differential equation is now y prime x prime is equal to f of x. Okay, so if you want a vector, use vector notation in 2 dimensions. That's how you write it. So input output, and then the question becomes really big, and that is what is linearization in dimension two? Okay, so we'll work it out. Not the actually to understand what linearization is, we actually need calculus. Okay, so we're not gonna do that. We'll just imagine that as if we already did it somehow by some magic, and then what we end up with is like we did over here, a linear differential equation has been acquired, and let's just deal with it. So we know that we can simplify, so let's imagine that we can imagine that we already have, and therefore we have a linearized differential equation. So what does it look like? Not too complicated. So I'll get here. Here. So that's a linear one. That's what a linear one looks like. Okay, general one. This is the general right here. So some kind of function. So this is y prime, x prime is equal to f of. I did have that a minute ago. So the general case is this. That's the general. And then linear. The two functions f and g are linear. Okay, meaning what does it mean? It means that they are both. There is no multiplication. So both x and y emerge in the linear fashion, cx plus dy. Okay, so that's linear, and that's linearization. So once again, how we do not ask, but you can guess that what if you're not there yet, we have with 3, it is requires some partial derivatives. Okay. So f of x, y, how do I find a and b, right? Think about it. So a function of 2 variables, f of x, y, and I need to linearize each of them. And how do I linearize it? So that the terrain is a surface of function of 2 variables. You linearize, replace it with a plane. What's the plane made of? If you got that far in calculus 3, it is the made of the 2 partial derivatives. Okay, so at that point, replace 2 partial derivatives, give you 2 directions for the plane, creates a plane. That's a linearization. Okay, so if you care to know how, but let's just suppose that that is done somehow. Okay, somehow. Okay, so we have a linear system on the right, and this is the one we will be dealing with primarily. And as you can see, it's way simpler. It is has only 4 numbers to worry about. We also might expect that maybe look at how similar it is to this one, dimension 1, right? Coefficients, nothing but coefficients of our x and y, but not naturally. So that's bad news. It's complicated. Good news is that it does capture once again, the quality of behavior will be captured, and it will have only these, once again, three possibilities, non-generic possibilities, and so nothing more complicated than that will emerge. So settle point, either sink or source maximum. Okay, so that's the good news. If you do one point at a time, one equilibrium at a time, then our linearization will be perfectly good. Okay, so once again, just to point out you what qualitative analysis means in dimension 2. This is the table that we produce depending on the sign of f and g. Okay, so the direction of the arrows, and therefore directions of the coordinates are going that way. Okay, in one particular direction. So these are the four pictures in this one, in the four cells are the generic. So this is still generic. All of these are generic. The only non-generic is in the middle, where both of them are zeros. And so then the way the trajectories behave around that point is what we want to establish in direct. Okay, so we assume that everything is zero, and once again, this is the classification of equilibrium in dimension 1: stable equilibrium, unstable equilibrium, semi-stable equilibrium. Okay, so by that logic, well, what makes it stable? Because everything goes towards it. What makes it unstable is it goes away from it. What makes it semi-stable is that some going in, some going out. So that kind of idea is still survives. So all in, all out, some in, some out. Okay, so if you take these description and you can translate them into dimension 2, we're still going to be using them. Okay, so and these are a few pictures right here. You can tell which one's which. Classify. So these are, by the way, also done with Excel. If you look carefully, you can actually recognize the arrows. Okay, so what kind of equilibrium? It is an equilibrium. So in the middle there is a stationary point, and there is a spiral. Okay, so what kind of equilibrium is this? It is stable because
They all go.
going towards, and this one away from it. So it's unstable. What about this one? What? Semi-stable because some in and some out. There is another equilibrium that's really special, like this. Oops, what happened? I lost it. Yeah, so it crashed. Oh, nearly connect. Okay, so here's some randoms. Okay. Yeah. Semi-stable, but the last one is special because it does not fall into any of the three categories. It's cyclical. It's cyclical, and so an example that we had in the beginning, that's the periodic behavior. So then it's, what is it? It's nothing goes in, nothing is going out, everything just dances around it. Like with the predator framework. So each of these three has a name. Things such as center, focus, and settle points, and so we'll get into that. All of them emerge in the linear case. Okay, the simplest case is the linear case, and so we can hope to linearize it and produce a differential equation like this, system of differential equation like this. and then without wondering how we get there. So linear differential equations are such a big part of the theory that if we just take care of that, that could be sufficient for us. So the challenge is really not the, as I said, linearization. It requires calculus 3, but rather actually dealing with linear algebra is the challenge. Okay, so vectors to begin with. So everything becomes vector in this analysis. So once again, it is x prime is equal to f of x, and once again, all of these are vectors. Time is still a number, but the rest of them are vectors. So we combine x and y into one, and if we would have x, y, z if we have 3 variables. And so in other words, what we're missing is still we need to learn a lot more linear algebra, so to be able to handle this. Okay, so once again, okay, that's a typo right here. To be able to handle it. Okay, just once again, not linearization itself, but just a linear system as simple as it gets, simpler than the predator-prey model, which is non-linear. And so we'll see what happens. We'll see what happens, but we are progressing to the next. Okay, we're going to the next lecture note set. Linear algebra and vector trees. Okay, so we set a differential equation aside for now and concentrate on vectors and specifically matrices. Okay, so let's so no differential equations for the time being, but nothing, no calculus. It's algebra in its literally, even though it means nothing but algebra for a while, and hopefully at the end you will be handling the algebra in the same manner as you do with you handle numbers. Okay, so all right, so vectors. What's the vector on the plane? We talked about that already. So it's 2 numbers, no more, no less. Notation is 2 numbers either in triangular brackets or in the form of a column. Okay, so column is preferred. Okay, so a vector field, which is once again what ODEs look like, it is a point with points with a vector. So that's an ODE. But if we were to abandon them, then what we end up with is just a bunch of vectors. All of them originate at the origin. Okay, and from the origin, it goes to some point AB, and that is exactly the vector that we call AB with triangular brackets. Okay, so they are not points anymore, but they're subject to algebraic operations, and we execute them component-wise. Naturally, in addition to the algebra that you know, algebra of vectors, when we do the certain constructions, it is very easy to actually carry out the operations. If the vectors are given explicitly, you just carry them out component-wise. And since we stick to dimension 2 almost exclusively, this is all there is. Really, it's 2 operations only. Scalar multiplication and addition, so which means that we do not multiply vectors. We do not divide vectors. We don't do sine cosine with vectors. So like I said, it's not just we're doing algebra. We're doing algebra minus all the complicated stuff. No exponentials, no complex straight functions, no, not even multiplication. So it's linear algebra means that there are these 2 operations, period. So the challenge lies not in those operations, but rather in the in dimensions. So too many dimensions here. Okay, so once again, so what I want to do next is produce a problem that is rather than kind of something tangible, physical, but rather something about the data. So not dissimilar from the problem of predator-prey, which was the point of which was to realize that x and y's are some possibly unrelated quantities, and they just vary in some way that is somehow influence each other. So we're not doing any dynamics right now, but we are dealing with data. Okay, so that's the problem that a linear algebra problem typically looks like this. It's about mixtures. So we have 2 types of coffee, and one is costs $2 per pound, and the other one $3 per pound. And now the question is, how do we produce a blend that is 6 pounds of weight and $14 total cost? Okay, so once again, all problems like that are solved by introducing variables. We introduce the variables, x to be the weight of the Kenyan coffee, y is the weight of the Colombian coffee, then the total weight is x plus y is equal to 6, and 2x plus 3y is the 2x is the cost of the Colombian coffee, 3y is the cost of the Colombian coffee, and so together 2x plus 3y is supposed to produce 14. So the first equation is about the weight, and the second equation about the cost. Okay, so at this point, you can just go ahead and solve it. It's really not much of a challenge. So you do algebra. And so for better or for worse, the fact that it is easy, it's so easy that we're not going to be even doing it. Okay, so I do hope that you find solving this equation easy. Just, substitution, move stuff around and you're done. So the example itself is just introduced as a way to have functions emerge from nothing. Not really that dissimilar from predator prey, which we took the number of foxes, the number of rabbits, and combined them into a vector. Okay, so we're doing a similar thing here. We combine x and y into a vector, which is the blend is not single numbers to it, right? Each blend is two numbers, one for x and one for y, and then the rest is really coming later. So once you realize that x, y is that vector, is then you realize that this is just the conditions that we impose on that vector. Okay, so doesn't matter how we did it, we may have guessed, but nonetheless, the answer is 4 and 2. So that's easy to do it within middle school. Within middle school, you pretty much can do this problem. Okay, but we're not going there. We're looking for vectors. Okay, so not only in we realize that probably there's a vector here, x, y, blend. What I want to say here is that blend is a vector, x1. That's what the blend is. Two numbers determine the blend. No, the blend, not proportions. You see, it's about total weights. Okay, so we take this. So how do we reinterpret? Having this in mind, how do we reinterpret my system of equations? This one. Okay, and we know that we have to combine, not like this, but rather I cut the two equations here as they are originally into two, so two equations separately. But that's not what we're after because we have both x and y on top and bottom. Let's cut it this way instead. Okay, so like this. Okay, so actually 614 is another vector right away that emerges. So if we have some algebra in the first row, okay, so this is a one vector, and that's another vector. Okay. One vector, we can combine any two numbers into a vector and whatever if we want to. So if I say that 614 is a vector, which actually has very different from x and y, by the way. The blend is a vector x and y, and both of them are in pounds. Okay, if I formed vector 614 right here, then actually 6 is pounds, but 14 is dollars. Okay, so it's a different vector. Nonetheless, we can see how we can try to combine things together. Naturally, in linear algebra, it's simply more motivated by things. Why do we look for vectors when things are so simple? Because what if there are more dimensions? What if you have a blend of 3 coffees? What if it's not about coffee? Maybe it's about a portfolio of 1,000 stocks, and you want to combine them, produce something that you want. So it makes sense to combine numbers into vectors. So we take this an easy example when we can actually handle it without computers. And so like I said, the equal sign, the y equal sign, that's what it means for two vectors to be equal to each other is this. Component wise, they're equal. So there are two vectors. What does it mean for them to be equal to each other? It means that the first components are equal, the second components are equal. Okay, so that's what you see at the bottom here. And so once again, 614 is what we want. It is a very, very nice way to combine them into one vector. So xy is then what we want to find, what we need rather, or which one is we need? We need to know to produce the The result is required 6 and 14, so somebody, your boss comes to you and tells you, we want 6 pounds of $14, cost $14 of the mixture, okay? So, so that's at the end of this computation on the left, which the end result should be 614, and so we're more working backwards from 614, we're supposed to find x and y. Okay, so so that already some progress has been made, but we can do more than that, and that is combine x's with x's and y with y's. Okay, so that vector on the left can be, so that's the meaning. Doesn't matter what the meaning is, we will keep in mind what the meaning is. It's the equations split into two, but the other one is more simpler. It is a really simpler rather than having many equations, many variables. Let's combine them together. So this is what I do after a vector on the left or after on the right. This is what I can do. I can do actually algebra of vectors on the left. Okay, so just like I had I had one equal sign and that replaced two equal signs. Over here I have two addition signs. Okay, replaced with one. Why so? Because I have addition of vectors. It's available to me, so I'm doing it. So that's what that vector on the left is written with all of those things. It's actually these vectors added together. Okay, so how do we add that? How does it work out? Because it is down component wise. So 1x with the meaning of what's at the bottom, 1x plus 1y. That's the first component, and the second component is 2x plus y. Okay, so we're kind of moving backwards. So we certainly quite clear on what operations mean on vectors, but here we're moving backwards. We're already seeing the outcome of certain computations, and then we realize that what we're looking at are vectors. Okay, so all right, so then that's one simplification. Do you see another simplification here? That will be number 3. Simplification. So once again, in the same sense, simplification. So the things will become compact.
X vector times y.
That's right. That's right. So the logic is the same. So 2 equality sign, 1 equality sign, 2 additional signs, and here I have the whole 4 multiplication symbols. Or well, multiplication by x. Let's do it this way: multiplication by x, multiplication by x. Okay, and here multiplication by y, multiplication by y. So let's combine them together, and then we realize that indeed vector 1, 2 on the left is multiplied by x, and then vector 1, 3 is multiplied by 1. Okay, so that's exactly what it is. So once again, we unfold the operation that is as if it has been already carried out, but we're moving backwards and realize that indeed we have actually 3 vectors, 1, 2, and 1, 3, one multiplied by x, the other one by y. These are the 2 numbers, and then it's supposed to produce 614. Okay, so that's literally the payoff of operations that we have on that we introduce on functions on vectors. Those 2 operations, they are really emerge here from this simple linear algebra problem. Okay, so then all right, so that's let's rewrite this vector equation using the column notation. Okay, 1, 2 times x, 1, 3 times y is equal to 614. Okay, so once again, the symbols, look at the symbols are the same. Multiplication symbol is the same as with numbers. Addition equal signs are the same symbols, but they refer now to vectors. Okay, so that's a challenge really for the most part here. So once again, look at these vectors. They are all 2-dimensional vectors. And then naturally, that's the only way for them to be able to carry out operations. So if you start with a vector of dimension 2, you can multiply by a number. It's still a vector dimension 2. You add 2 of those, so you get once again a vector 2 vector. These are all 2 vectors. That's the abbreviation. And then they all have the same units. By the way, all these vectors have the same units. Number of the first number refers to the weight, and the second one refers to the cost. Okay, so when you multiply by x, that's when the that's when the hold on a second. X is a number. X doesn't have a x. Doesn't have a unit. Hold on a second. So number of pound, per pound, X is the price. So X is, so once again, these are the weights, these are the costs. But then, X
X
is
was one type of coffee and Y was,
dollar, what?
X was one type of coffee and Y was the other type?
The amount, yeah, so it covers the pounds. Yeah, X and Y, are pounds, and then, pounds, and one is the, so hold on there, I'm not, I'm on here, hold on a second, pounds, okay, so, no, it's not weight in pounds, it is weight, uh,
By container.
What?
By container.
No, not the container, what I'm thinking here, we multiply by one, so we just add, the multiplication here is really, these ones are, I would say this is not really the weight as much as it is, I think that these are unitless probably. So unitless, and so when I multiply X is in pounds already, okay, so, and then, it can go either way, I'm just thinking which way is better to go, is X and Y are in pounds, measured, or they are, unitless, and I'm thinking that they're probably better as pounds, because they are actually different pounds, right, so X the pounds of the Kenyan coffee and Y pounds of the, Colombian coffee, so it's not, they actually have different units. So how do you convert them together? Then you multiply them by these, unitless operations, but they are converted from the specificity of particular, kinds of, coffee to the one that is generic and they can be added together. So this is kind of subtle point, and I don't think I want to, go into that. So let's just say that everything is, measured in weight. The second one is easy because then it's the price, and so the second, the 2 and 3 are actually, per pound, right, per pound. So it's not really cost, but as much as this price. So the price is $1 per pound, right? The price is $1 per pound, and you multiply by the number of pounds, and you end up with the cost. Okay, the total cost. So yeah, so like I said, so 2 and 3 are the prices. These are the prices. Prices, okay, and then, so multiplication is meaningful when you multiply by X and Y, and X and Y are in pounds, so a price is measured in dollar per pound. You multiply by a pound, you end up with dollars only, and that gives you the cost. Okay, makes sense? Okay, so, so naturally in mathematics, we try to ignore the units as much as possible. But sometimes they're just useful in the sense that they are, might point out mistakes that you make, especially when you try to, if you look at X, Y, and you look at 614 and you look at 1, 2, they seem to be, they are of the same size, and they may be they're of the same nation, but they are. So for example, you will never add X, Y to 614 because of the, difference of units. If you don't pay attention to the units, then you might end up with these, operations. Okay, so, so then the solution of the equation is literally, find X and Y. So if you, now we're going to the actual equation, this is the equation. So one equation, 2 unknowns, okay, and then you need to find them from the equation. So equation for X and Y, naturally that doesn't sound right. How can you have one equation with 2 unknowns? But it is actually, there are 2 equations hidden in it. And then if you combine X and Y into one, then, so it makes sense. So 2 unknowns, 1 equation. That would sound strange, but if not for the fact that we could actually, have 1 unknown. Right, unknown meaning X, Y. If we combine X and Y into 1, then there will be 1 unknown vector and 1 equation, vector equation. That would make sense. Okay, so, but that's before we get to that later in a minute. But right now, let's look at what we're facing here. What is the, let's go trial and error. Okay, trial and error, we can change X, we can change Y. Okay, as we're changing X and Y, so it's vector 1, 2. is multiplied by x, which stretches it. Okay, 1, 3 is multiplied by y, also stretches it. And then we add them together. Okay, so it's the two vectors that stretch back and forth, and then all the possible sums of them will produce a result which is supposed to hit exactly 614. Okay, so this is called linear combinations. Okay, linear combination. So two vectors of linear combination of what? Of 1, 3, of 1, 2, and of 1, 3. Linear combination meaning that exactly that you just multiply by a number and then add together. Okay, so this is what the picture will look like. So 1, 2, and 1, 3 are the bottom left. Okay, so all right, and then what we're doing here, we are going to giving a stretch to the one vector and giving the stretch to the other vector and then add them together. Okay, we're supposed to, however, done in such a precise way that giving different weights to each of them so that we produce 614. The outcome should be 614. As you can see, if you look carefully, it's not halfway, right? So if I take equal amount of 1, 1, 3 and equal amount of 1, 2, then the sum or linear combination in that manner would be go between them. But that's not the case. So we know that we're going to give those numbers, the weights to the two vectors should be different. And then indeed it turns out 1 is 2 and the other one is 4. Okay, so once again, this is the problem that is we're trying to solve right here. Find xy. Find xy is on the left. So find the exact extensions of those two vectors, red and green, in such a way that together they will produce 614. And the solution of that problem is right here. So we already know. So I double the green vector. I quadruple the red vector. Together it does produce 614. Okay, so that's the problem is solved. So it's just an illustration of what the problem is, regardless of how the problem is actually solved is secondary. It is very important to understand what is the scope of possibility. The space of possibilities is the whole plane, as a matter of fact. So if I start changing these weights 2 and 4 and put anything else there, these are x and y. So say, what is it? So this is x times 1, 3. Okay, and then over here I have maybe y times 1, 2. Okay, and then add them together. So by varying x and y, I'll get the variety of vectors that will cover the whole plane, or at least the first quadrant. Okay, so and out of those we have to find the exact combination of x and y that would produce 614. Okay, so that's the challenge. That's the challenge. So how do we figure it out? And the answer is coming up shortly. It's we form a function of two variables. A function of two variables, two inputs, two outputs. So that's what we want to see here is a combination of x, y gives you what? Combination of x, y gives you what? It gives you a point on the or vector on the plane. Okay, so let's call it u v. Say so. Yeah. So maybe this is x, y. Is your particular combination, and the answer is UV. That's the sum. So 4 variables present at the same time. X, Y as the input and UV as the output. Okay, specifically, that's how it's computed. So U component is this, and V component is that. So we still remember where it comes from. Remember, U refers to the weight, and V refers to the cost. Okay, so that's the space of what we want. Both weight and cost is on the right, the output, and the input is x and y. So it makes perfect sense. The all possible mixtures, which are determined by x and xy, produce on the right two numbers. That's on the left. Input is xy, the weights, right? And output is weight, total weight plus the, or not plus, but rather, and okay, so the problem is quite clear is that if we know x, y, we plug it into the formula and we know the output, the weight and the cost. Makes perfect sense, right? So if we know the two weights, we know the prices, the formula is simple, we plug it in and we find the weight and the cost. It's the inverse problem. Remember the word inverse from calculus, inverse? Backwards. We know the output and we need to find the input. Okay, so 614 is the output of our function, given by this formula, and we need to find where it comes from 614. So for how do we get 614 from xy? So literally, once again, we go in xy plane, all the blends are on the left, and all the, not all the blends, but rather all combinations of the two copies are on the left. At each point has two numbers, x and y, and then all the outputs, the blends, that include their price and their weight. Okay. So, a problem, similar problem you can think about the, any other mixture you can think of if the coffee doesn't ring a bell to you, nutrition. Nutrition, and then on the left you have the ingredients as well as somewhere, and you also, how much calories or carbs or whatever in each of the ingredients that you're using for cooking. And then the function on the left produces the total calorie, total carbs, total fat, whatever. Okay, and then naturally that's how, probably there are apps like that, no problem. Gives you, if you enter the ingredients, and it will give you the output of what your meal is supposed to produce. Okay, how much your intake is going to be. But also the same app would have the opposite problem. Also, this is how many carbs I want to have. This is how much calories I'm ready to take, and then you got to go backwards and find the menu pretty much, or ingredients of that your meal is supposed to be made. That's the linear algebra. It has so many problems that you can solve with them. But for us, we are sticking with low dimensions. It's 2 and 2, and we're not going to go beyond it. We need to understand that that's what the function is. It is what it comes up later on, and that which is it is a transformation. It is a transformation from one plane into the other. Okay, so in transformations, you might remember every function is a transformation, so you can think of things such as flip, shift, stretch, rotation. All of these are possible transformations. So from our goal then is, from looking at the equation, we have to determine what kind of transformation that is. Depending on what transformation it is, and this we are keeping an eye on where we're coming from. Remember this is what we're thinking. Okay, that's fine, because of f of x. Depending on what that f or transformation it is, the classification of the differential equation will be different. So, okay, so once again, what's here is the mathematical part is here is that the function of two variables, two inputs, two outputs, which is, in other words, is a vector to vector function. Okay, and then we just need to understand them. Okay, so once again, we need to go back to find value xy that gives us 614. Okay, so that's how we rewrite it. This is how we rewrite it. So our function x is the input, but this time x is xy. Where's my xy? Xy. And on the right is the b. 614 is what the outcome that we expect. And then 1, 2, and 1, 3, those numbers are simply the setup. They determine the function f, and our control is naturally x. We can have any blend that we want, and then we're just watching the output, and we're hoping that 614 will produce good. So this is really what follows is analysis of these. So we have a bunch of vectors already present. We have 3 vectors we extracted here. Or at least initially we had 1, 2, 1, 3, x, y, and 614, 4 vectors. Okay, turns out there are a little bit fewer vectors here if we just do our job right. And that is what we do is just we collect all the coefficients of x and y and put them in the table. And that we call the table a matrix. Okay, so 1, 1, 2, 3. 1, 1, 2, 3 is describes f, right? Look at it. xy is the input, 614 is the output, right? So yeah, so input, it's possible for the input. This one is responsible for the output. So then what's left? Is this is f, the function. Okay, so these are the combination of 4 numbers. Very easy, right? Because everything is linear, so it's easy. Those 4 numbers combined together in the right order they determine our function. Okay, and we do, as I said, we just put it in the table, 1, 1, 2, 3, that's what it is. So literally, we put x's before y's in both the lines and just read the coefficients from it. 1, 1, and 2, 3. So that's my matrix. That's the matrix of our function, or a technical term is, it is a matrix of our linear transformation. Okay, so once again, as you can see here, if you look carefully, the difference in notation is we omit the parentheses. Okay, so if you that's what separates the function in general, and then that's the functional notation when we use parentheses, and when we use matrices, we do not, and so that's so there is no multiplication sign. So function here and matrix there. So function works any function. I could have chosen different function here. If something more complicated happened here, I could have x squared, I could have sine y, anything you can make up, and they also surely will produce differential equations of different kinds. But we are concentrating on linear ones. So that's why matrices are available as a very convenient tool. Okay, so let's see what we've got here, and then so how you can see how the operation, which we now call the multiplication. Okay, so that f followed by x, what is it? It is actually a multiplication of a matrix by a vector, which is what you see on the left here, and you can see on the that's on the right. On the left, you can see how the that operation is executed. You multiply. Look at the first row. Look carefully what happens here. The first row is multiplied by x1. Okay. Well, multiplied in this weird way. So 1, 1, xy, they are multiplied like this. And they added together. And that's supposed to produce 6. And then you do the same with the second row. So that's the operation on matrices. How a matrix is multiplied by vectors. Naturally, the dimensions have to be matching. I do hope that you've seen this word before, and you really should. It's called the dot product. Anyone? Dot product. So we are looking at the dot product. So if we take my matrix, and that 1, 1 is a row, but it's a row of my matrix, but it's also a vector. So if I take vector 1, 1 and a vector xy, what I execute here over here is the dot product. So a multiplication, component y is followed by addition. Okay, so in other words, that the vector multiplication, the dot product is nothing but just a building block of our new operation. Okay, so remember we had 2 operations on vectors, but now we throw in dot products of vectors. Okay, that might still come up, but the main operation is how a matrix is multiplied by a vector. So that is the definition, just for the record, how we multiply a vector of 2 by 2 vector and 2 by 2 2 vector and a 2 by 2 matrix. So as you can see, they align together appropriately, and then concentrate, and we produce a new vector, also 2 vector, by multiplying, doing dot product. So red. AB times xy gives me ax plus by. That's the first term of my vector. And then I do CD, the second column by xy, which gives me cx plus dy. And that's the second entry in my vector. So this thing is the same. Okay. So that's the matrix, the algebraic version that we did. It's remember that what it is. It's nothing but, if it looks complicated, remember what this is. It's an abbreviation. Everything is an abbreviation after all. So we introduce vectors to make things more compact. We introduce operations in order, once again, them to be not to be spread out. And because everything is linear, abbreviation is actually possible. So we would not be able to speak of multiplying something by xy unless that something is actually involves nothing but scalar multiplication. Okay, so multiplication like this. So there could be no sign, there could be no x squared here, or that would all out of the question. So linear algebra deals with the simplest imaginable situation, and that's what makes it all possible. Okay, so once again, notation, two different notations. Okay, so now we have in front of us what we understand what we study. We're studying beyond just algebra vectors to begin with. Okay, with those two operations, we're studying linear transformations called linear operators, and they're all given by two matrices. Okay, so that's our goal. So let's think of them as transformations. So they're to make them somewhat more tangible. If they look abstract, especially in the abstract space, the spaces with of those properties is an abstract space. It's not a physical space. So it helps to actually, once we form the two planes, think of them as how one is transformed into the other. Okay, so physical. So that's what the transformation is, and if you might, where's my example here? So R1 to R1, we didn't talk about that, I don't think. Transformation of a line to a line, so let's make a quick stop in dimension 1, rather than jumping straight to dimension 2. So in dimension 1, the transformations, what are the transformation of line to a line, the simplest ones? Shift, okay, shift literally, so like this, shift. So this is my y-axis, this is my x-axis. So I don't do this. Okay, we're not doing right now. We're not doing the graphs. Why not? Aren't we doing? And you can see why not. So this is we're not doing this. No, because we cannot do this here. We have to develop in one-dimensional case. We have to develop ideas that would be applicable to dimension 2. And in dimension 2, if I try to I have two planes. I have two planes, each of which has two coordinates, two components. So what's the total dimension? What? 4, right? So when we're doing one-dimensional situation, there are only one. In one, it's 2, and we draw it on the plane, and we're very happy with it. But when you go to high dimensions, it's 2 and 2, and we cannot be 4-dimensional. And knowing that's 4-dimensional doesn't help. We cannot visualize anything well in that case. So that's why we do not do graphs anymore. That's the graph. Okay. Instead, we're doing this x and y. Okay, we're transforming x into y, and once again, you can shift x along y. What else? A flip. You can like a pencil. So like this. So it was this, and then I did this. That's a flip. What else? Stretch, shrink. So the shift is adding, flipping, multiplying by -1, stretching, multiplying by 2. So all of these are linear operations. And now they all match. They also all reemerge in the two-dimensional case. So once again, you have two planes next to each other. You can shift in an infinitely many directions. Okay, you can flip in an infinitely many ways, and then you can stretch. Okay, uniformly or non-uniformly, that's also nice. And then finally, we can, something that does not appear in dimension 1, we can write. Okay, so all of these are linear operations. The variety of things that can happen are already huge. So that's why we stick to linear as much as we can. So, okay, so that's one-dimensional. Let's examine the simple operation. In fact, the function that we already have seen. So, each of the components of my function is a function of two variables itself. Look at it. Two functions, f and g, each of which is a two-dimensional. So if you do calculus 3, you're actually doing this. Okay, functions of two variables, each of which has like partial derivatives, has linearization. Its graph is a surface. Okay, it's all good, but now we have two of them. So they together, f and g, are actually constitute my function. Okay, so I know where h, x, y goes. X, y goes to 2x minus 3, but also under the second function goes to x plus 5y. Okay, so if we were to combine together into one, that's what my vector algebra is. So x, y goes to vector uv, which is given by 2x minus 3y, and x plus 5y. Okay, so If I were to write it I could write it now in the matrix notation, right? So once again, I take those coefficients that were present at the very beginning, 2, -3, and x, and 1 and 5, and put them in a matrix. Okay, and it's just nothing but more compact representation of this. So this is long, and this is short, but it's the same thing. Okay, so we can abbreviate, so that's why we do. And if it looks complicated, it's sometimes abbreviations are maybe too compact to understand, but it's worth it. It's worth it. And then if you do any kind of algebra, that's how it works out. So let's look at some of the operations of two-dimensional space. A flip. Okay, so this is the flip. XY becomes negative XY, which means that it is a horizontal flip. X goes to negative X, nothing happens to Y, that's a horizontal flip. So you might remember that in calculus, transformations of graphs of functions, anybody remembers from calculus, pre-calculus, exactly that, flipping, stretching, shifting graphs of functions, that's how we just execute it. So now you know what's behind it. Mirror image, what does the picture in the middle, the bottom, what does it remind you of? What's the issue from calculus, from pre-calculus? What?
Like horizontal line test, sort of.
No. Look at the picture at the bottom shows you I have a graph written on a piece of paper, and it has two branches, green and red, and then I do this. And one lands on the other, one half lands on the other. What do we call such a function? With two identical branches, like this mirror image of each other. That's what it is. What do we call those functions? I bet you know, just.
Yeah.
What?
Well,
Well, it is a parabola, yes, but a parabola is a specific curve with that property.
Symmetric.
Yes, it's symmetric, but specifically to the mirror symmetry, but once again, there's a word for it. It's called even functions, remember? So it is the function, the graph of which under this transformations transform into itself. You flip the graph, you don't flip the graph, you flip the plane, and the graph lands on itself. So in which case we have an uneven function. Okay, so as you can see, it's multiplication by -1. Let's produce a matrix. That's what the matrix looks like. That's what the matrix of the horizontal flip looks like. So it has, look at it, two zeros. And then in the second row, there's a 1 because nothing happens to Y. And we have -1 because X multiplied by -1. Okay, you can confirm that in the last row. It is indeed that matrix is a horizontal flip. Okay, so vertical flip, the opposite. Now the Y goes to the negatives, becomes negative. Okay, so once again, that's what the flip looks like. And the matrix has a -1 in the bottom right, because once again, something happens to Y, nothing happens to X. And those two zeros indicates that there is no interaction between X and Y. So the central symmetry, okay. Both X and Y become negative or flipped in sign. So you flip the sign, you flip the graph. All what? Function is called. What's odd? Yes. So even has mirror symmetry, and the odd function has the central symmetry. Okay, so once again, where does it come from? It comes from this flip. So it is flip about the origin, which means that as you can see -X, -Y, it means that we have two flips, horizontal and vertical, combined together, and that's the total result is a combined flip, and it has this in its matrix has two -1s on the diagonal. Okay. So these are a very productive approach to look at a lot of things that you saw in calculus 1, and now you can see them here. So a vertical stretch, Okay, x multiplied by k, so the function is very simple, so you have to ask why do we even need this, but there will be more complicated ones. And so this is the horizontal stretch, this is the vertical stretch, and you can combine them together if you want to. And rescaling is when everything is stretched proportional in all directions. It means that the matrix has k's on the diagonal. So for example, to double the picture, you have 2, 0, 0, 2. Okay. What about disproportional stretch? Naturally, you have a disproportional numbers. Okay, so that will be stored if I started here with a nice star. If I go with 2, 0, 0, 3, it will be doubled horizontally and tripled vertically, so it will be stretched. This is, by the way, you can execute it totally with Paint. Microsoft Paint, anyone, right? So it has all of these operations, it has all the flips, it has the stretches in form uniform and non-uniform. Okay, I'll stop here. We'll continue next time. Our question?
Do we have class on Thursday?
Yes, why not?
That's the full name, I was just.
No, yeah, we have to have one.
Okay.